Um, Thank you for giving me this opportunity to discuss about our results. So my name is Koutoulaki. I'm a postdoc at the University of Leeds. And today I want to talk to you about gravity data of 51 and spatially resolving the CO overtone emission. Just with a short introduction on the low mass star formation. So we have the collapse of the molecular cloud. So due to conserving angular momentum, we have we have the protostar, and due to the conserved angular momentum, we have the creation of a circumstellar disk. So in the first phases, we have the envelope being basically much larger than the mass of the star, where we cannot really observe it at near infrared wavelengths. But as the envelope dissipates and we go through the class 2 phase, the star becomes visible at near infrared wavelengths, and we can study the disk and in some cases the jet. If we want to look closer at the disk, here is a drawing of a circumstellar disk. So we have the central source here. So we have a gaseous disk around it, because we don't expect any dust grain to survive that close to the star, because the dust sublimates at 1500. And then we expect the dust to be present in the outer part of the disk, forming the outer disk. There have been many studies addressing the properties of the outer disk, but there are very few concerning the gas properties of the disk, the so-called inner gaseous disk. And this is mainly because of the small scale, spatial scales we're talking about. This region of the disk, though, is really important because all the main accretion injection properties are taking place, and this is where planets may form as well. And the energy released in this part of the disk influences the whole balance of the disk. There are many lines that could be seen in this part of the disk. So we have hydrogen combination lines, like the bracket gamma line, which we have heard before as well, but also molecular lines like the CO vibrational emission at 2.3 micron. In order, though, to spatially resolve this region, we need near interferometry. So for this study, we're using VLTI gravity. I guess most of us know, so I'm not really going into detail, but basically our resolution is much increased by combining the 4 telescopes of the VLT, going to milliarc-second resolution. And by using interferometry, we can actually study in this part of the disk the dust continuum, so the star and the disk. As we've seen before from the previous talks, we can also study the bracket gamma lines. In some cases, we can also spatially resolve Freund lines, which are higher transitions, but we can also see the molecular lines. So mainly I'll focus on this part of the disk, because as we've seen before, the origin of the bracket gamma line is quite controversial. So we've seen cases that it traces magnetospheric accretion, but you can trace a wind. So if we really want to study the disk, the CO emission is an ideal tracer. The only disadvantage on that is that the CO is quite rare. So it's not seen in many young stellar objects. So we can, for example, in T-Tauri stars that we heard before, there are only 3 of them that exhibit this CO emission. And in the case of Herbig stars, it's around 17% and slightly more, around 20% in the case of massive young stellar objects. So to continue, basically to work on this emission, what we did was to develop a CO model, so a model in LT conditions. So we created a single temperature cone densities of the CO, so a ring. We also developed it to work as a disk as well. Basically, here's just an example of the spectrum on the top of a T-Tauri star, and then underneath is just the model overlapping on the observations. So what we wanted to do is we wanted to use this modeling and combine it with our interferometric observations to extract more information on the inner properties of the disk. And here is a bit more about 51F. So 51F is a Herbig AUV star. It has a mass of around 4 solar masses. It has rich molecular and atomic lines, and it has a compact dust component. So the reason we chose this target was because we knew before that it exhibits C overtone emission, which is quite bright. Here's an example of amber data in 2008 of this source, and we can see that they marginally resolve this CO emission. So this is the visibility. And they found that the CO emission originates really close to the star, around 0.15 AU. But with our gravity data, so here we can see the gravity data. So on top, we see the flux. So we have 4 vibrational transitions, and then we see 2 epochs of observation. So we have here 12 visibility and 12 differential phases. So the first thing we can see is have in mind that 0 visibility means completely resolved, 1 means unresolved, so a compact source. So the whole system seems to be quite compact. So we have visibilities around 0.8. But the most important thing is that we have a strong differential phase signal. And why I mentioned that, because here, for example, we can see visibility versus spatial frequency. And if we take our visibilities, for example, here, the visibilities for the continuum, we can see that we have a plateau on the longest baselines around 0.8. And by fitting just a simple geometric model, for example, a Gaussian that we can see here, is really difficult to constrain the properties because we don't really go lower to the longest baselines. Here on the right is an example of the CO, so basically subtracting the continuum of the visibility. So these are the CO visibilities. So because we could not really extract any information from that, really precise information from that, what we did was to model the CO spectrum. Here is the black dots is the spectrum, and the red is the model. And what we can do with that, so by having this model, we can actually we create an intensity map. So here we can see the intensity map. Here's just an example of the first plan head, and here is just 3 points where the intensity map is extracted. And why I show you this is because the CO doesn't behave like a normal line, though we have the bracket gamma line, where we have a blue shifted to the peak and then a red shifted part. And we have basically a better separation of the velocity. But here we can see that on the blue shifted part, we actually have the most of the emission on one part of our ring here. But as we go to the peak and to the red shifted part, we see a blend. And that's mainly because of the J transitions and the blend between the P and the R branch as we go to the right, basically, of the line. So what we see here is the differential phase signal overplotted on top with calculating the photocenter shifted placement from these intensity maps. And by taking, for example, this case and calculating the photocenter shift for different position angles, we can actually see that we expect to have the major displacement along the major axis of the disk and the minor displacement along the minor axis of the disk. So, and also by doing so, we can actually calculate the size of the emitting region because it will be along the major axis of the disk. But we can also have information on the geometry of the system, so the position angle and the inclination as well. And what we find from this is that, for example, the radius, so the CO originates from a radius of 0.1 AU from the star. We find an inclination of around 70 degrees and rotational velocity for around 140 kilometers per second. What we can note here is also the fact that it's quite difficult to constrain the properties, especially here we see the temperature common density, and that's because the J transitions are quite optically thick, and because our spectral resolution is quite poor, it's really difficult to have better constraint, though it's really consistent with previous studies and also at higher spectral resolution that the conditions that we need are warm and quite dense gas. So in the resolution that we're talking about, it doesn't really make much of a difference when we're trying to calculate our displacements and the size. Of course, there are things to be done. What we're trying to do now is to actually combine higher spectral resolution observations along with interferometry. And this is something we're working now on in some cases of high mass interstellar objects, for example. And also we're trying to do similar things in Herbig stars as well. And just to conclude, there's no doubt that the CO emission is a really good tracer of the disk. The problem is that it's not as common, and this is something we're also trying to investigate. And unfortunately, there are not that many models of, there's no models of the inner disk, and this is also something we're working on to try and understand why we see this CO emission in some cases and why not in others, and what are the conditions that are needed to really have this emission. What we find is really this CO overtone emission comes from a dust-free region, really, really close to the star. So in the case of 51 is at 0.1 AU from the star. Another thing that I think I have demonstrated is the fact that although the system is quite compact and could not really extract some information from the visibilities, we can actually use the diffraction phase signal to give us much better spatial information and also velocity information of the system. And that shows that it's a quite powerful tool to use. Stay tuned, because soon we'll have more data on combining also high spectral resolution with interferometry, and hopefully we'll have more results on and understand more about this emission and why it's formed. So thank you for your attention, and I'll be happy to take any questions.
Okay, thank you very much, Marie. Do we have any questions? Oh, yes, sir.
Yes, Stefan Gross. At the current spectral resolution, it's kind of unavoidable that we average over the many bandhead lines. And based on your models, do you think they all come from the same region, or is there a significant gradient in what radius in the disks they come from?
So in this case, for example, for the first three bandheads that we did this analysis, they seem to more or less come from the same region, because I think we don't have enough maybe also spectral information to understand that. But there are cases that we see in also some in high mass vessels, for example, that you see more of a plateau, and also that it seems that we need a disk gradient to really also fit the results. Yeah.
Thanks.
Perhaps I can ask a question. So you mentioned that we also see this in massive young stellar objects. Is it more prevalent in the more massive systems, or is it just kind of sporadically found across the mass ranges, the presence of the CO overtone?
Yeah, so it seems that it's more prominent in these cases, around more maybe 20%, but still it's quite low in comparison to the study that has been done. But it's still not clear if it's just the area that you need in order to be able to see, or if it's just an inclination effect as well, but we don't see. There are a lot of things we need to think more and why this is happening. Yeah.
Cool. And yeah, just out of interest, what spectral data are you looking at in comparison, in combination?
Cryo data.
Okay.
Yeah, because then you can really spatially resolve the J components, and this can really gives you more information.
Okay, great. Thank you. Any more questions from the floor or online? Okay, well, in that case, we can thank Maria again and continue the conversations on Slack.